In this video, I give an introduction to GMM estimation. GMM estimation relies on assuming that the data and the model parameters satisfy a certain moment condition. Here the function g is the expectation of a function f. Here we have that theta is a k-dimensional vector of model parameters. Theta 0 denotes the true parameters. F is an r-dimensional vector of functions. Wt denotes the model variables. And Zt denotes the instruments. So this is a very general framework, and we will show throughout this course that a lot of the models and estimators that we have considered so far lies within this framework of generalized method of moments. A crucial assumption throughout this topic is that the model parameters are identified. This means that the function g takes value 0 if and only if we evaluate the function in the true parameter vector. This ensures that there is an unique vector theta 0 that solves the equation system. In practice, the function g is unknown, but we can approximate the function by considering the sample average of the functions f. The idea is now to use this function gt to derive an estimator for theta. We consider three different cases. Recall here that gt is r-dimensional and that theta is k-dimensional. In the first case, we have r equal to k, meaning that we have just as many moments as parameters to estimate. We denote this case the exact identification case. In this case, we can simply put gt equal to 0, which gives us an r-dimensional equation system. As we have just as many unknowns as equations, this system has a unique solution, which we denote the method of moments estimator. In the second case, we have r greater than k, meaning that we have more moments than parameters, and we denote this case the over-identification case. In this case, we cannot find a solution to the equation system, but it turns out that we can still find an estimator, which we denote the GMM estimator. The last case is the case where r is less than k, meaning that we have less moments than model parameters, and we denote this case under identification. In this case, there will be multiple solutions to the equation system, meaning that there will be no unique estimator. Hence, we cannot empirically identify the parameters. Next, we will consider a simple example in the case of exact identification, and the example is based on the well-known linear regression model. Recall the well-known regression model where yt is given by xt prime beta plus epsilon t. Here we assume that beta is k-dimensional and that we have a k-dimensional regressive variable xt. First, we consider the case where xt and epsilon t are uncorrelated such that the moment condition is satisfied. In this case, we have that the model parameters are yt and xt. Given that the moment condition is satisfied, we can consider xt as the instruments. The model parameters are beta. Moreover, the function f is given by xt times the residuals, meaning that the function f is simply xt times yt minus xt prime beta. We note here that if we evaluate f in beta 0, the true parameter vector, then we get xt times epsilon t. In this case, we have k equal to r, meaning that we have k parameters, and r moments, meaning that we have exact identification. The sample moments are simply given by the average of xt times yt minus xt prime beta. And setting these sample moments equal to 0, we can solve the equation system and find the method of moments estimator. And we note here that the method of moments estimator coincides with the well-known OLS estimator. Next, we consider the case where the moment condition is not satisfied. In this case, we have less moment conditions than model parameters, meaning that we have under-identification. This is an unfortunate situation because we cannot estimate beta consistently by the method of moments estimator. Lastly, we consider the case where we've got a set of instruments, a set t, which we assume are uncorrelated with the error term. We assume that set t has the same dimension as xt, namely k. In this case, we can consider yt and xt as the model variables and set t as the instruments. Our function f is now the instruments times the residuals, and we have the moment conditions g of beta 0 that is equal to 0. In this case, we again have r equal to k. So we have just as many moment conditions as parameters, and we have exact identification. We set up the sample moments, which are just given by the average of set t times the residuals. And setting these sample moments equal to 0, we get a k-dimensional equation system. Solving this, we get the method of moments estimator. Note that we have here assumed that the average of set t times xt prime is invertible, meaning that the instrument should be relevant. Note here that the method of moments estimator coincides with the well-known IV estimator. Thank you for watching.